Okay, welcome to Let's Get to the Marks. We're going through AQA Chemistry A-Level Paper 2, Question 8. This is a request from Cho 2000. Sorry if I got the pronunciation wrong. Let's go. This question is about citric acid, a hydrated tricarboxylic acid. Its formula can be represented as H3Y.XH2O. A 1.50 gram sample of H3Y.XH2O contains 0.913 grams of oxygen by mass. The sample burns completely in air to form 1.89 grams of carbon dioxide and 0.643 grams of H2O. Show the empirical formula of citric acid is C3H5O4. As always, when working in an exam, underline key points or get out your highlighter and highlight some of the key points. So the first thing to work out here is we've been given mass of carbon dioxide, we've been given mass of H2O, so obviously we're going to want to work out the moles of those. Now we're dealing with this hydrated compound, which is H3Y.XH2O. We know that it said completely burn in air, so we're combusting it in oxygen to make carbon dioxide and water. If we can just work out the moles of carbon dioxide and the moles of water, we'll know that will be equivalent to the moles of carbon and hydrogen in our hydrated compound. So let's work out the moles of carbon dioxide first. 1.89 grams divided, by 44. And that equals 0.0429 moles. You can round that to 0.043. And then if we do the 0.643 grams of H2O divided by the MR of H2O, which is 18, we get the number of moles of water. So now if we know the moles of carbon dioxide and the moles of water, we can work out the moles of carbon atoms in H3Y.XH2O and the moles of hydrogen in H3Y.XH2O. And you're going to score 2 marks straight away out of the 5 for working out these moles of carbon dioxide and water. So now we've got the moles of carbon dioxide and water. Let's work out the moles of oxygen. You can see at the top we were given 0.913 grams of oxygen. So if we divide that by the MR, it's really the AR of oxygen because it's an atom. We get 0.057 moles of oxygen atoms. So let's write these all down. We have 0.0429 moles of carbon based on the fact that that's how many moles of carbon dioxide were formed. And we've got 0.0357 moles of water. Now we have to double this because remember, each water molecule has 2 hydrogen atoms in it. So I'm going to get double the amount of hydrogen atoms on the left than I do for the amount of water molecules. So we're going to do 0.0357 times 2, and that's going to give us 0.0714. And that's how many moles of hydrogen atoms you have. And obviously the water has H2O inside it, so you're going to have double the amount of hydrogen atoms in the empirical formula. Okay, now for the oxygen, we've got 0.057 moles. We worked that out by dividing its mass, which they gave us in the stem of the question. What we need to do now is we need to divide these all by the smallest to get them into a ratio. And the smallest amount of moles is 0.0429 moles. So let's divide them all to get into a nice ratio. So relative to the others, we have 1 of carbon, 1.66 of hydrogen, and 1.33 of oxygen. We now need to turn these into whole numbers. It's an empirical formula. We need integers. So what you're going to do is try multiplying them by different numbers until you get close to 3 whole numbers. And if we times them by 3, we're going to get 3 for C. We're going to get 4.98 for hydrogen. That's more or less 5, so we can just put 5. And we're going to get like 3.99 for oxygen, which pretty much is 4. And that's your empirical formula, 3, 5, 4. And you've just proved it. Well done if you got that right. Moving on, 8.2. 3 gram sample of H3Y.XH2O with an MR of 210 is heated to constant mass. That means we've evaporated all the water. The anhydrous H3Y that remains has a mass of 2.74 grams. Show, using this data, the value of X is equal to 1. Right, first of all, we've got 3 grams of the anhydrous. That's the H3Y.XH2O. We're going to subtract from it, sorry, the hydrated. We're going to subtract from it the anhydrous, which is just the H3Y. Essentially, once you take away the anhydrous, which is the dry substance, from the hydrated wet substance, you're left with how much water was evaporated. And we evaporated 0.26 grams of H2O. So let's go ahead and work out the moles of that. That's 0.26 grams over 18, we've got 0.014 moles of H2O. Now, why are we working out the moles of H2O? Because essentially, what is X in these hydrated substances? Well, X is just the ratio between the anhydrous part of the substance, the H3Y in this case, and the H2O, which is on the other side of the little dot. So we're just working out the integer that X is equal to. So essentially, another point we can take from this is that the anhydrous substance, the moles of the anhydrous, H3Y, are equal to the moles of the whole hydrated substance. So if I want to work out H3Y, I can just work out the moles of H3Y.XH2O because those moles are equal to each other. So I'm going to do 3 over 210 because they've been lovely enough to give me the mass and the MR. And that's going to give me the moles of 0.014. Sound familiar? That's because it's exactly the same as the moles of water. So therefore, if the moles of the anhydrous substance is equal to the moles of the water, the ratio between them is 1. So X is 1. We have 0.014 moles of H3Y and 0.014 moles of H2O. Once again, how did we know we have 0.014 moles of H3Y? Because we had 0.014 moles of H3Y.XH2O. Right, let's move on.
Keep moving on, keep moving on, keep moving on, keep moving on.
So moving on to the last 2 marks of this question, we've got 8.3, complete the IUPAC name for H3Y. Figure 5 shows the structure of H3Y, and we can see it right here in front. So we can see, first of all, there are 3 carbons in the main chain. Well, that's where we get the name propane, okay? Then we can see there are 3 carboxylic acids, one coming off the first carbon, one off the second, and one off the third in the main chain. I've circled the name in pink here. Here are the 3 carboxylic acids. So this has already been done for us, the propane 1,2,3 tricarboxylic acid. So what's the bit we're missing? The bit that's incomplete, they haven't mentioned the hydroxide group. And which carbon does it come off of? It's the second carbon. So the name is 2-hydroxy-propane 1,2,3 carboxylic acid. Now 8.4 says state the number of peaks you would expect in the C13 NMR spectrum for H3Y. So let's get into it. Okay, for the last part of this question, we just need to work out how many different carbon environments are there. That's what you do for C13 NMR. So we're going to rub all of this stuff out, okay? And just get that name back there. I hate this sometimes. Right, there we go. I'm going to leave that propane circled. So we still got that answer there. Right. We've got how many different carbon environments? Well, let's look at these 2 here that I've circled with a 1. These 2 carboxylic acids are symmetrical, so they're identical environments. They both have the same groups coming off of them. Now we can see if we go to the next carbon in line, we've got a carbon down here with the final 3rd carboxylic acid, which is down below here. This carboxylic acid here is not symmetrical to the others. It's a unique carbon environment. So this is the 3rd carbon environment. Okay, it has different groups attached to it than the others. And then the final carbon here in the middle, this is the final carbon environment. It again is not identical to any of the other carbon environments. So the answer is there are 4 carbon environments. Hope you did well. This video was requested by Cho2000. Anyone else has got a video to request, just hit me up in the comments and let's get to the marks.
still here? It's over.